Okay, so first question we'll take a look at is looking at a expression that has trig in it and then converting it to an expression without any trig and just algebra. Does anyone remember which trig function we start with? The inside or the outside?
Inside.
Which one?
Inside.
Inside, yep. So we always start with the inside trig function. And do you remember what we set the inside trig function equal to? Because it's inverse trig. We know that inverse trig is always going to give us an
Angle.
So since inverse trig always gives us an angle, we're just going to set that equal to a Greek letter. Yep. We don't know what theta is, but we know when we do inverse tangent, there'll be some angle. Now we want to get ready to draw this in a right triangle, but we need to rewrite it with regular trig. How do you get rid of inverse tangent? Yeah. You do what? We take tangent of each side. So take the tangent of what's on the left. Take the tangent of what's on the right. We haven't solved anything, we've just rewritten it. So now it's x equals tan theta. Now we have to draw a diagram where that is true. So let's make a diagram. Put theta in the diagram. And now we know that tangent is equal to x. What's the definition of tangent? Opposite over adjacent. So we need to label the opposite side and the adjacent side so that when we divide opposite by adjacent, we get x. So what could we make the opposite side? Yeah, x. And what could we make the adjacent side? 1. So now the tangent of theta is opposite over adjacent, and this picture matches that equation. All right. What side are we missing?
Hypotenuse.
Hypotenuse. And how could we find the hypotenuse knowing the other two sides? Yeah. Right. We'll just do the Pythagorean theorem. So x squared plus 1 squared, and then take the square root. Now we know all three sides. What trig function is it that they want us to figure out using the diagram we just made? Sine. Right? We're going to figure out the sine of what I just underlined is that picture. What's the definition of sine? Yeah.
Opposite over hypotenuse.
Opposite over hypotenuse. So mathematically, if you plug a number in for x here, and you plug a number in for x here, you will get the same answer now. But what do we have to do to fix that so it's written properly?
We can't have a radical in the denominator.
Right. We don't want to have that square root in the denominator. So what would we do so it's not in the denominator? Yeah.
Multiply the top and the bottom of the square root.
Yep. So multiply the top by the square root. And when you multiply by it in the bottom, you get x squared plus 1. So there's the final answer for the formula without any trig in it. Any questions on that? Okay, let's try this one. So same idea, inverse trig on the inside, regular trig on the outside. Which function do we start with? Yeah. Inner. X over the square root of x squared plus 1. And what do we set that equal to? Yeah. Theta, because we know inverse trig is always going to give us it's going to give us an angle. And now I need to rewrite it with regular trig. So what do I have to do on both sides? Yeah. Take the sine of both sides. That gives me x over the square root of x squared plus 1 equals the sine. Now draw a diagram where that is true. What's the definition of sine? Opposite over hypotenuse. So we need to make the opposite x. We need to make the hypotenuse square root of x squared plus 1. Now, how do you get the third side? Yeah, Pythagorean theorem. Anyone think they can tell me what the third side would have to be there? 1. Yeah, it would have to be 1. Because it would be x squared plus 1 squared, add them up and take the square root, and that's how you find the hypotenuse. So, yeah, that's perfect. Okay, so we've got that. Now, they want me to take the cosine. Definition of cosine. Yes. Adjacent over hypotenuse. Okay, so we've got adjacent over hypotenuse. So mathematically, if you plug in a value for x here, and in the original problem, it will come out the same. But can someone give me my final answer without the square root at the bottom? Yep, Travis.
Square root x squared plus 1 over x squared plus 1.
Perfect. Yep, that's how you do it. Okay, so next question we're going to look at is solving a trig equation graphically. And we are going to solve this over the interval from 0 to 2 pi, because it does say to do it over a given interval. So solve exacts from 0 to 2 pi. If we're solving over a specific interval, do we put plus the period times n on the answer? No. Period times n means to find all. We're not doing all, we're just doing 0 to 2 pi. Okay, so we have two choices. Do we want to get this equal to 0 and then find roots? Or do we want to leave it the way it is and do a y1, y2 intersect? Which way do you guys want to do it?
No first.
Find the root, do it by getting it equal to 0? Okay, so if we want to get this equal to 0, what would I do on both sides?
Subtract.
Sure, subtract 1. Okay, now we only have to type in one thing in y1. Type this in. And where it equals 0 means where it crosses where? Yeah. X-axis. That's what we're looking for. All right, so sine 3x. Make sure that minus 1 is on the outside of the argument, not inside. And because they said exact answers, what should I do on my calculator? Because this is the only way to get the exact answer. Oh, second one? Okay, I'll take a look. Probably tomorrow I'll take a look at it.
All right, thank you.
You're welcome. Yeah, exact answers. How do we want to set the calculator to do those? Yeah?
Don't you have to make sure the node is in degrees and then set the radian by hand?
You have to do it in degrees first. Okay? That's the only way you're going to see the nice answer. And then you got to change to radians at the end. So what should I set for a, oh, I'm already in degrees. what should I set for a window? Because they gave me the window in radians. I need degrees right now. Yep.
0 to 360.
Okay, so let's do 0 to 360. We're in degrees. Check what you typed in. And remember, we're looking for it crosses the x-axis. Okay, so it looks like it's going to cross the axis, a little fuzzy there because of the tick marks, but how many times does it look like it maybe touches the axis? Yeah? 3. So what we're going to do is second calc. I'm going to find the maximum because what I want to figure out right now is, does this go above and then come back down? Right? If it does, then there could be 2 answers at each of these spots. Let's see what happens. Okay, the maximum value was 0. Does that mean that it crossed the line? No, it means it touched it and then it bounced back down, and it looks like it's doing the same thing everywhere. So one of the zeros is, what should that be? The calculator is estimating it, but it's really what number? Yeah, 150. That's one of our answers. I'm going to call that T2. That's 150. Now, you could do maximum for the other ones, or you could just do 0. It doesn't really matter. So I'm going to try 0 on this one. I think it's going to be 30. Well, let's see. Well, it says it's 29.999998. So we're going to call it 30. And T3, well, these look very equally spaced. How far apart are 150 and 30?
120.
They're 120 apart. So I'm going to guess this next one is probably 270. Should always double check it, but it helps to have an idea of what you think the answer is. And let's see if it's at 270. And we get 270. Now, because they said the exact answer in radians, we're like 90% of the way there. We just have to change these. What's 30 degrees in radians? Yep, pi over 6. Now, what do you multiply 30 by to get 150?
5.
So 5. So this is 5 pi over 6. And what do you multiply 30 by to get 270?
9.
9. So this is 9 pi over 6. Or, when you divide by 3, 3 pi over 2. So that is the exact answer in radians over the interval 0 to 2 pi. If they said find all solutions, I would have put plus the period times n. What would be the period of sine 3t? Yep. 2 pi over 3. Yep. Formula is 2 pi over b, and in this case, b is 3. Right, but I'm not putting that because they didn't say to find all answers. All right, so next question we're going to look at is simplifying a trig expression. So the first thing we want to do is simplify what's being squared. Now, remember, that is a FOIL. Okay, we have to FOIL to do that. So if it helps, you can write it out. Secant plus cosecant times another secant plus cosecant. And then the times cotangent, I'm not even going to look at that right now. Okay, so let's do this out. What's secant times secant give you? Yeah,
Secant squared.
secant squared. Okay, I like squared. Sometimes we can throw a Pythagorean identity in there. We might have to look up and see if there's one that would help us. And then we have secant times cosecant, secant times cosecant. How many of the secant times cosecants do we have? Yeah, 2. So 2 secant cosecant. Secant cosecant. And lastly, cosecant times cosecant. What does that give me? Cosecant squared. Okay, and that whole thing is still multiplied by cotangent. All right, so I don't really think a lot nice is going to happen. Things are going to cancel here. So let's just change to sines and cosines. Okay, let's start with secant. Does anyone remember which trig function do you flip to get secant? Yeah, cosine. So which function would you flip to get secant squared? One over cosine squared. Okay, so there's the first one. Secant, we just said that is 1 over cosine. How about cosecant? How do you write that? Yeah.
1 over sine.
1 over sine. Okay. How about cosecant squared? What would that one be? Yeah. 1 over sine squared. And lastly, how about cotangent? How do you write that one in terms of sines and cosines? Yeah, cosine over sine. Okay, so again, that was number 13 in the homework, and that's all you can really do. There's not a lot nice that's going to happen. I mean, I guess you could distribute this out to all 3 of those factors and see what happens. But that's not really going to give us much value for the kind of problems you need to know for the test tomorrow. So if you understand what we did there, distributing, changing to sines and cosines, those are 2 good skills for the test. Okay, so we're going to try a verify, which means you have to somehow turn one side into the other. We're going to start with the left-hand side, and we're going to try to change it into the right-hand side. So one technique we have is change everything to sines and cosines. What trig function is that? 1 over tangent. Yep. Cotangent. And what is that if you write it as sines and cosines? It's cosine over sine. Okay, so we've got that. How about tangent? What's that if you write it with sines and cosines?
Sine over cosine.
Sine over cosine. Okay, so we've got a cosine in the top, cosine in the bottom, sine in the top, sine in the bottom. Everything cancels and we're all done, right? No, why not? Yeah, it's addition. That's not multiplication, so nothing cancels. So we've changed everything to sines and cosines. Bless you. What do we do next?
Common denominator.
Common denominator. One way to find a common denominator is to take the two that you have and multiply them together. So sine times cosine is my common denominator. All right. Now, do either one of the fractions up above have sine, cosine in their denominator? What do you think, Travis?
No.
No, we got to fix both of them. What do you have to multiply top and bottom by in the fraction on the left to make this denominator that denominator? Yep,
Cosine.
cosine. Cosine. Cosine. What do you have to multiply top and bottom by for the fraction on the right to make this denominator that denominator?
Sine.
Sine. Sine. Sine. Now, each of the denominators is cosine sine, or sine cosine. Same thing. So we've got the common denominator. What's cosine times cosine? Yeah.
Cosine squared.
Cosine squared. And what's sine times sine? Yep.
Sine squared.
Sine squared. And now what happens there? Yeah.
The top equals 1.
The top equals 1. So you have 1 over sine times cosine. Now, if I write that, is what I'm going to write now? I want to know if it's the same thing as what's up above. Are those the same thing? Yeah. It's just like if I had 1 over 3 times 7, and I write it as 1/3 times 1/7. Yeah, absolutely. That's the same thing. Now I'm going to look at each one separately. What's 1 over sine? Cosecant. Times, what's 1 over cosine? Secant. Now let's go back up and see if we had a cosecant times a secant on the other side. Cosecant times secant. Yep, exactly. So that's it. That's how you prove it. All right. So to simplify this one, if you start changing to sines and cosines, that would be not a fun process. There's a lot of things that are squared there. When I see things that are squared, I'm going to try Pythagorean identities right away. Okay. What do we have to do with that minus that's in front of that other set of parentheses? Let's distribute it. So when we're done distributing it, we're not going to have any parentheses left. So minus tan squared and minus cotangent squared. That's our first step. Now, I'm going to regroup these a little bit and just put them in a different order, because we can add and subtract in different orders as long as we're careful how we rearrange it. I'm going to rewrite this as secant squared, and I'm going to put the minus tangent squared next to it. Okay, so I just moved it. I wrote it earlier in the problem. And then I'm going to write down the second one. And the last one I'm going to keep right where it is. So from this step to this step is just a reordering of the 4 terms. I want you to focus on this from that. Secant squared minus tangent squared. Does that look like anything? That we talked about today. Kind of like what?
Sine over 18 minus sine over cosine 1/6.
Yeah.
Like the second equation down from what you, it has both tan and secant in it.
And what do you call those things? Yep.
Identities.
What kind?
Oh, Pythagorean?
Pythagorean, yes. What's underlined in blue and green are both Pythagorean identities. What is secant squared minus tangent squared? One, yes. If you subtract tangent squared to the other side, it would say secant squared minus tangent squared equals 1. How about cosecant squared minus cotangent squared? That's also 1. Because if you bring that to the other side, you get 1. So what's the final answer to that problem? 2. So that's one where all the trig cancels out, and you just end up with the number 2. That's it. That's the final answer. Okay, so the next three really is just evaluating inverse trig function. So we just type it in on the calculator. What do we have to do to make sure we do these problems the way the directions say? Yeah.
We change it to radians.
First thing we have to do is change to radians. I'm in degrees. Okay. And now, how would you type in inverse sine 0.3? Yep.
Second side. And then
Second sine 0.3. That's it. Okay. Second cosine, negative 0.4. And second tangent, 1.8. That's all there is to it. Any question on those? What if I said inverse cosecant of 5/2? Do you have an inverse cosecant line? No. So anyone remember when you do inverse trig, what does it always come out to? Always gives you an angle. So let's temporarily don't think about it as inverse trig. How could you get rid of inverse cosecant? Take the cosecant. If you take the cosecant of what's on the left, what do you get? 5 halves. Now take the cosecant of what's on the right. We still don't know theta, that is the goal. But if you know the cosecant is 5/2, you know another trig function automatically. What function is connected with cosecant? Sine. If the cosecant is 5/2, what's the sine? 2/5. So kind of show you a pattern that happens. Now get theta back by itself again. What would you do on both sides? Yeah.
Sorry, I was just.
take the inverse side.
Take the inverse side. So if you're looking at it and you're like, well, wait, we just ended up with theta all by itself again like we had originally. Yes, but there's a big difference. That is something we know how to type in. That is the same thing, but we don't know how to type it in. So whenever you have to do an inverse trig function that you don't have a button for, all you really have to do is flip that fraction and change it to the one you do have a button for. That's the shortcut. Or you can go through those steps every time to think about it. So inverse sine of 2/5. That's the answer to that question. Yep.
So like 1 over inverse sine wouldn't work
No,
for this?
nope, can't do that.
So you would have to like completely flip it?
You just flip what's inside.
Okay.
So like if I said, what's the inverse cotangent of 3/8? You don't have an inverse cotangent button. But cotangent is connected to which function? Tangent. So let's do inverse tangent instead. And you wouldn't do 3/8, you do 8/3.
Okay.
These are the same thing. Yep. All right, so last one we'll take a look at is finding the domain and the range of 2 inverse sine 3x. First thing is we need to know the originals. So let's do the domain first. What is the domain of inverse sine? No transformations, just regular domain. -1 to 1. So normally the domain of the inverse sine is -1 to 1. Any question where the -1 to 1 comes from? Comes from the range of the original, -1 to 1. All right, so we have -1 to 1. And what is that 3 doing? Compressing it which way?
Down by 1/3.
So which direction? Horizontal or vertical?
Horizontal.
Yes, horizontal. So that's a horizontal compression. It's going to compress everything down 3 times as much. So if we originally went from -1 to 1, what are we going to go to if we compress that 3 times as much? Yep. -1/3 to 1/3. Okay, the long way to figure it out that I showed you, if you don't remember that, you put the argument in the middle. You set up a compound inequality with the originals on the left and the right, and then you solve for x. People remember that for Monday? Then you divide everything by 3. Gets you the same result we just got, -1/3 to 1/3. Okay, range. What is the range of inverse cosine? Just the basic range. If you don't remember the range of the inverse, think of the domain of the original.
-pi/2 to pi/2.
-pi, those red lines. -pi/2 to pi/2. What's that 2 doing?
Vertical stretching.
Yeah, it's a vertical stretch by how much?
2.
By 2. So we're taking the range and we're doubling it. So what would you get if you take -pi/2 to pi/2 and you double it? -pi to pi. Yep. That's it. That's how you find the domain and range. So you have to know the originals to find the new ones. The inverse cosine and inverse tangent are very similar.